Today's topic is going to be choosing energy sources of fossil fuels. So what's the big deal? Why do we need to choose different energy sources? Although energy may be obtained from the direct combustion of fossil fuels, a more convenient form of energy is electricity. It can be carried from one place to another, it can be switched on and off, and it can be used as a source of energy for many different devices. Furthermore, a large percentage of the fossil fuels that we burn are for electricity to power our homes and other electrical devices. Black coal is number one. Natural gas, number two. Brown coal. So brown coal is coal that is not completely coal yet. It's going through the process of being coal. It will require several thousand years more to become coal, become the coal that is black coal. So it's just not as far down, and it hasn't been compressed, and it hasn't endured the pressure and as much oxygen-free environment as black coal. And furthermore, when it combusts, it doesn't combust as efficiently as black coal. So 1, 2, 3. Fourth is hydroelectricity. Fifth is wind. All right, so those are our tops. Oils below this: solar photovoltaic cells, bioenergy, and geothermal. But as you can see, coal is number one, so is natural gas. So the combustion of these fossil fuels. So the combustion of these fossil fuels is important for us to study. Fossil fuels. Fossil fuels are coal, petroleum, and gas. And they're called fossil fuels because they were formed from animals, trees, small plants, the sea organisms, vegetation that lived from millions of years ago. Coal was formed from the combined effects of pressure, temperature, moisture, and bacterial decay on vegetable matter over several 100 million years. Decaying vegetation progressively became peat, very soft and mushy, lignite, crumbly brown coal, bituminous coal, which is the hard black coal, and anthracite, very hard coal. Over this period, the moisture content dropped and the carbon content increased, as anthracite is the highest quality of coal. There is peat. It's the youngest. And then there's lignite, with brown coal. Bituminous coal. It's hard black. And then fourth, anthracite. Very hard coal. While petroleum and natural gas have their origins in marine life buried in the sediment of oceans millions of years ago. Heat, pressure, and action of bacteria changed this residue into petroleum and natural gas. So coal is the world's most plentiful fossil fuel. The main elements in coal are carbon, so it's about 50 to 98% carbon, and 3 to 13% hydrogen, oxygen, and a very small amount of nitrogen and sulfur. It also contains moisture and inorganic material that remains as ash when coal is burned. As coal is formed, it underwent changes in composition that made it a more efficient fuel. Here's a figure that I found that describes the processes of coal and its inevitable formation of solid black coal, anthracite. So first it begins as decaying vegetation, forms to peat, time passes, it becomes buried, increasing temperature and pressure. So brown coal is first made, then various different levels of coal quality, and it's becoming more and more carbon. Victoria generates more of its electricity from brown coal, which is about a quarter of the heat content as black coal. We're going to need to know this for later on in the week, but it's good to know, and we're going to discuss this in class in a group discussion. Brown coal can have up to 30% oxygen content, a relatively low carbon content, 60 to 75% when dried, and a high moisture content, say 30 to 70% moisture. By a process called destructive distillation, coal can be converted into many useful products such as briquettes for heating, coal gas, sulfur, ammonia, benzene, coal tar, and coke. Coke is used in the reduction of iron oxide to iron. So it's coke means carbon, it's pure carbon. In addition to electricity, coal may be converted into gas or liquid fuels. These can be transported and used more cheaply and conveniently than solid coal. Now let's shift and talk about petroleum. Petroleum, or crude oil, is a sticky black substance composed of a combination of many different hydrocarbons. It must be refined before it can be used. Octane, which is C8H18, is the major component of petrol and may burn in air to release energy according to the equation 2C8H18 liquid plus 25 oxygen gas. I'm going to bring the equation down here. 16 carbon dioxide gas plus 18 H2O. Liquefied petroleum gas, that's LPG, is a hydrocarbon fuel that consists mainly of propane and butane. It is non-toxic, non-corrosive, lead-free. LPG, like any gas, can be liquefied under pressure, and when allowed to vaporize, it expands to nearly 300 times its liquefied volume. This is why LPG can be stored as a compact liquid, but it's burned as dry gaseous vapor. LPG is popular with many motorists, especially fleet vehicle owners, because it is an economical energy source. Although LPG conversion costs for cars running on petrol are quite high, more people may make the conversion or buy new car designs to run on LPG as petrol prices increase. Natural gas. Natural gas is an important source of alkanes of low molecular mass. Victoria has large reserves of natural gas in the Gippsland Basin. Typically, natural gas is composed of about 80% methane, 10% ethane, 4% propane, and 2% butane. The remaining 4% consists of nitrogen and hydrocarbons of higher molecular mass. Natural gas also contains a small amount of helium and is one of its major sources. Methane is the major constituent of natural gas, and it burns with a hot, clean flame. Methane, of course, when you burn it, it's going to be CH4 gas plus 2 oxygen gas goes to carbon dioxide plus and that's carbon dioxide gas plus 2 water molecules. Since natural gas is lighter than air, it disperses in air. However, it is explosive in certain concentrations. So a safety measure incorporated by gas companies is to add an odor so that the leaks may be readily detected. Natural gas itself, though, it's odorless. Since in chemistry we're talking about delta H and heat capacities and so forth, let's look a little bit about the energies associated with these different hydrocarbons, these different fossil fuels. Let's kind of look at it in a, let's say, the fossil fuel. Since we've been looking at energies associated with making and breaking bonds in enthalpy, it might be wise for us to consider looking at these. Natural gas, and let's look at the kilojoules per gram. Notice that it's not moles. When I do a multiply to the -1, that really means divide by, so kilojoules per gram. So natural gas, it has 54 kilojoules per gram. Petrol has 48. Black coal is 34 and 16. There's a considerable difference between these.